Welcome to lecture 4A, Introduction to Cache Memory. In the fourth module, we are going to learn about memory hierarchy. We will have detailed discussions on cache, DRAM systems, cache coherence and quick introduction to how hard disk also works. Last few weeks, our lectures were on how processor pipeline works, what are hazards, what are the different types of scheduling like compiler scheduling and dynamic scheduling at hardware, out of order execution, speculative execution and all. One of the another important aspect of computer architecture is all about storage or something that deals with memory. We will be focusing our attention on three types of memory. One is on-chip memory, that is cache memories. Off-chip memories, they are DRAM, and off-board memories, they are talk about hard disk. Today, we will start with the fundamentals of cache memories with the lecture title Introduction to Cache Memory. This slide is about pipelined RISC data path. We have started our discussion in this course with a 5-stage instruction pipeline consisting of instruction fetch, instruction decode, execution, memory access and write back stages. Now, we are trying to understand what is the role of memory in this context. We can see that here we have a memory component and here also we have a memory component. The first memory component is accessed by every instruction and that is called fetching of an instruction from the memory, and we have seen that to take care of structural hazards we are having separate memory for instruction as well as data. So, instruction fetch uses memory and memory access stage also, when you have load or store instruction also, we are going to access memory and that is called your data memory. All other three stages, stage number 2, stage number 3 and stage number 5 are completely internal to processor, and the control logic and the register file together get the things done as for that particular instruction in decode, execute and write back stages. This graph shows over the years what is the trend in performance as far as CPU is concerned. So, you can see that there is a massive improvement in the performance of CPU, and we could see that there is improvement in terms of DRAM memory as well. But if you can see that there exists a huge gap, the rate at which the performance growth happens at the CPU side as well as on the DRAM side. Now, coming to the relationship of cache and pipeline, we have seen that in a 5-stage pipeline, the instruction is being accessed by cache and your data portion, whenever you wanted to access your load and store, that is also been interacting with the cache, and cache is being supplied from the main memory. So, the next couple of lectures, our focus of attention is on this memory aspect and the remaining. Let us try to understand what is the role of memory in this context. Programmers always want unlimited amount of fast and large memories. So, what we can do is we can create an illusion of making your memory very fast as well as your memory very large. It is impossible to make a very large memory at the same time it is fast, but this illusion can be created when you organize your memory as a hierarchy. So, here we have to understand what do you mean by a hierarchy. So, hierarchy means we have different levels of memory, different types of memory. Each memory has its own property in terms of speed, in terms of total storage, in terms of the number of reads or writes that you can do. Considering all these aspects, memories of different property are stacked one after another, and then processor is trying to access these memories based upon this requirement. So, when you create such a hierarchy of memory, we can provide a very large memory, or we can in turn provide an illusion that your memory is very large, at the same time it is going to be relatively fast as well, so that it can mitigate with the speed at which an instruction pipeline works. So, like what I have mentioned, when you go for multiple levels of memory, there can be differences in speed and the size of the memory, and your entire addressable memory space is typically kept in the largest, at the same time slowest memory. Keep the smaller and faster memories closer to the processor. So, this is the idea. Can you keep your smaller and faster memory closer to the processor and your slower and large memory just after that? So, this is the typical way how you look at. if you look at the CPU, it has internal registers. That's what we have seen. We have integer registers and we have floating point registers, which are marked as R for integer registers and F for floating point registers when we were going through the topics of instruction pipeline. So these registers are very fast, CPU can access them. Generally, wherever in our programs, we try to keep our operands in the registers possible, and you can see that it's not possible to have huge set of registers. Generally, the registers are in the order of few bytes, and accessing to registers is in the order of picoseconds. And then we can look into, we have multiple levels of cache memories. This is what we are going to learn today. And these cache memories are relatively very fast. And the L1 cache, which is the closest to the processor, will be in the order of kilobytes, and accessing them would be at the same order as that of accessing any other stage of an instruction pipeline. So it is during your instruction fetch stage, you are going to take something from L1 cache, and your mem stage also you are going to access something from the L1 cache. So your instruction pipeline is interacting with this L1 cache alone. This is the cache that we are talking about, where instruction cache is directly interacting. And then we have a little bit larger next level cache, that is called your L2, which will take close to 10 nanosecond or even slightly more than that. It will be roughly in the order of 256 KB or 512 KB, and sometimes it can be up to 1 MB as well. And some processors have the third level of cache, that is the L3 cache. So whatever be the case, we have a terminology which is called LLC, last level cache. Last level cache, it can be either L2 sometimes, if that is the last cache hierarchy that you have on the chip, or it can be sometimes L3 cache as well. So the whole thing is inside your processor chip. This is your chip. Now off chip, the first level of off chip memory is your main memory. It is also known as DRAM nowadays, because based on the technology that is being used, dynamic random access memory. And then we have the hard disk, that is for permanent storage. We can see that once you come to off chip, then your memory capacity is in the order of gigabytes and terabytes, and the access speed going to the milliseconds range. Looking at a different perspective of how this whole memory hierarchy looks like, I wanted to draw your attention to this. This is your CPU, which has registers through which I can read and write. The registers has read and write ports. Then you have separate I and D cache, which is your L1 cache, and then you have L2 cache, that is a unified cache, and then we have different chunks of main memory. Together we call it as the main memory unit. So we have seen what is the memory hierarchy all about, starting from the registers all the way to L1, L2, L3 caches, and then we go to main memory, and then finally the disk. Let us now specifically focus on what is cache memory technique. What are the fundamental principles by which cache memory operates, and how can you design a good cache memory? That are going to be the next focus points. A bit of introduction with respect to cache memory. Cache is a small, fast buffer between processor and the memory. And then what we do is, old values will be removed from cache to make space for new values. That is the whole idea of cache. And it is done with two techniques driven by principle of locality of reference. So what do you mean by principle of locality of reference? Programs access a relatively small portion of their address space at any instant of time. And what about temporal locality? If an item is referenced, it will tend to be referenced again soon. That is basically the idea of temporal locality. And then we have spatial locality. If an item is referenced, the item whose addresses are close by will tend to be referenced soon. Let us try to understand the principle of locality of reference in the context of a storage system. Principle of locality of reference has two subdivisions in it. The first one is called temporal locality. Let us try to understand what is this temporal locality all about. Assume that I am going to read one paragraph in a textbook. Now, if there is a very high probability that I am going to read the same paragraph again in the near future, I call it as temporal locality. Something that is accessed now, it is going to be re-accessed again. That is called temporal locality. In terms of program context, let me define like this. If I am going to access a location L at time t, then the probability of accessing the same location L at a future time t plus delta t is very high. Meaning, if I access a particular instruction or a data now, there is very high possibility that I am going to access it again. Before relating this concept to cache memory, let me draw your attention to the second component, which is called spatial locality. If I access a location now, let us say location L at time t, then the probability of accessing location L plus delta L, that is the nearby locations of L, in time t plus delta t is very high. So, if I access an instruction or a data, then the possibility of the adjacent instructions or adjacent data locations in the very near future, possibility of accessing these locations in the near future is very high. Now, let me put together temporal locality and spatial locality. When CPU is accessing a memory or CPU is requesting for an address, if it is not there, let us say in your cache memory, you go to the next level of memory, bring it. Why you bring it? Because there is a possibility that the same address will be requested by the processor in the near future, temporal locality. So, when there is high possibility of temporal locality, even though in my current reference I do not get it in my fast cache memory, I go to next level of memory, keep it in cache. Why I keep it in cache? Because my future access to the same address, it can be supplied from the cache. That is how I make use of temporal locality. Now, how am I going to make use of spatial locality? When I miss some location now, I have to understand that as per spatial locality, the nearby addresses will be requested in the future. So, rather than bringing only the requested word, let me bring the adjacent words also, such that when I bring something like a block or a bulk of data, my future request to adjacent locations can be serviced. So, in the concept of cache memory, when CPU is requesting for an address, I look in my cache if it is there. If so, I will supply it. If it is not there, I go to the next level of memory, bring a chunk of data and keep it in cache, such that any request to the same address or nearby address in the future can be supplied from cache, a faster storage. That is the whole idea of principle of locality of reference. Look at this graph. On the x-axis we have the clock cycles and the y-axis we have the address locations. So, let us say my program is relatively spread across address 75,000 to 85,000. These are the locations in the main memory where a particular program is currently accessing. Now, as time progresses, that is called x-axis, as time progresses, let us say at this particular time, this is the address somewhere around 78,000. That is the address where the program is currently working on. Now, as the time progresses, you can see that the address locations changes. Going up means it is going to higher address. And when you can see that in this region, the same address is being revisited, you come down to the same address. Similarly, in this region also, we can see that the same address is being repeated in the near future. That refers to temporal locality. If the address is being re-referenced in the near future, we call it as temporal locality. And if you look at this range, you can see that as time progresses, adjacent addresses are being accessed, and that is what is known as spatial locality. Let me consider two examples. Let us say two references. You imagine that each of the English alphabet represents an address. So, if these are the set of addresses that the processor is demanding, M, I, double S, I, double S, I, double P, I, you can find that there are a lot of S, lot of I that is being repeated. That is essentially what we are discussing right now. It is called temporal locality. The address S and I's are frequently re-referenced. Whereas if you look at this string, you can see that if every address corresponds to a location and A and B, they may be nearby locations, you can see that I am going to repeat the adjacent addresses. I am going to access the adjacent addresses only. That is called the whole idea of spatial locality. So, when I look into your memory concept, as we have mentioned, As discussed, we have processor, a main memory which is really big, and then we have a cache which is lying in between your processor and main memory. As and when processor requests for words, it contact cache and cache is going to supply them. So, the unit of transfer between cache and CPU is words. When cache misses something, it goes to main memory and bring a bulk of data, not only one word. Because of spatial locality, I will bring a larger unit of data, and that is what is known as a block. So, please remember this fact: processor contact cache first. If the requested word is there, supply the requested word. So, the unit of transfer between cache and the processor is always words, and the unit of transfer between cache and main memory is always in terms of big block of data. Some of the fundamental concepts that we see in cache memory is block or line, both are same. It is a minimum unit of information that can be either present or not present in a cache. So, you bring a block of data from main memory into cache, or you bring a line of data from main memory into cache. So, a block is either present or not present in the cache. That scenario, you cannot have part of a block that is being present in the cache. Then we will move on to hit. Hit is a scenario wherein an access to the data requested by the processor is there in the cache. If something is present in the cache, we call it as a hit. If whatever is requested by the processor is not present in the cache, it is not present, then it is known as a miss. And the time to access a cache memory block and return the data to the processor, if there is a hit, it is known as hit time. So, hit time means when the processor is giving the address, from that point, when will you get the word from the cache? So, given address, there is a process by which you come to know whether it is present in the cache or not. If it is present, you locate the corresponding word and then transfer this particular word to the processor, and that much time is known as hit time. And then we have hit rate. At the same time, we can define miss rate as well. It is a fraction of access that is found or not found in the cache. Now, let us try to understand what is parameter of hit rate. Let us say I am going to access cache 100 times, out of which if I am able to get the data, if there is a hit for all my accesses, then I call hit rate as 1. If I am getting hit only in 90 out of the 100 times that I am visiting cache, then it is called hit rate of 0.9, 90 divided by 100. And the miss rate is 10 divided by 100, 0.1. So, hit rate plus miss rate is always equal to 1. Ideally, we expect caches to have hit rate as close as possible to 1. And hit rate cannot be larger than 1. If every access is present in the cache, then it is called a hit rate of 1. Then the last term is called miss penalty. It is a time to replace a block in the cache with the corresponding block from the next level. So, what is miss penalty? Miss penalty means the moment, see, all your access in the cache may not be a hit. At times you get miss also. So, once it is a miss, that time onwards, you go to the next level of memory, bring a block of data, keep it in the appropriate place in the cache, and then supply the word. So, the moment cache miss occurs, from that time onwards until the missed word is ready in the cache, that is called miss penalty. The additional cycles required in processing a miss, that is called the term miss penalty. So, we have learned about what is a block or a line, hit, miss, hit rate, miss rate, hit time, and miss penalty. So, these are some of the very common terms that have been used in the context of cache memories. Look at this slide. Here we have a different interaction schematic of processor, cache, and main memory. So, what is given here is your processor. So, processor is a tiny fast CPU, the CPU to register. So, processor, the tiny very fast CPU registers has room for only very few words. In this context, I am taking 4 byte words. So, each of these registers can accommodate 4 bytes. Similarly, I have 4 such registers. Now, when you come to L1 cache, they are relatively small when compared to main memory, but bigger than that of processor registers. Assume that you can accommodate 4 blocks. Assume that
you have 2 blocks, each can accommodate 4 words each. So, I have 4 registers, each can accommodate 1 word. I have 2 cache blocks, each can accommodate 4 words, and then I am going to main memory. Main memory is big, but it is slow. It has room for many 4 word blocks like what you have. And we have seen that the transfer unit between CPU, register file and the cache is 4 byte words, whereas the transfer between cache and the main memory is 4 word blocks. Let us now look into the general organization of a cache. A cache memory is an array of sets. That is what you can see that there, these array of sets is been named as set 0, 1 all the way up to s minus 1, where you assume you have s sets. And this s can always represent as a power of 2. Let us say 2 power small s is equal to capital S. Now, each of these set has multiple lines in it or multiple blocks in it. So, you have E lines per block, and E is also typically a power of 2. And each of these lines we have, this is the data storage portion where I keep data that is been brought from main memory. You have few control section, control information, which is called a valid line or valid bit. One valid bit is there per line, and T tag bits is there for each cache line. So, when you have each cache line, this is the place where your data is located. You have a valid bit and you have a set of tag bits. Each cache line holds a block of data. That is what we have seen, and this block is also power of 2. So, what is the total capacity of the cache? The capacity of the cache is defined as C equal to B into E into S, where S is the number of sets, E is number of lines per set, and B is the number of bytes in each of the line. Now, consider the context that CPU want an address A, the physical address of A. So, once you get the physical address of A, that physical address is divided into 3 things: tag, set index and block offset. So, with this number of bits that is there for block offset, for set index and tag, it is easy for us to correlate what happened. So, S tells the number of set. So, if you have capital S, which is defined as 2 power small s, this will tell you how many bits are there in set index. And then your block is B bytes, which is 2 power small b. So, this will tell you how many bits are there in the block offset region, and the last portion is your tag. So, whatever is balance, that is called tag bits, and these T bits are being stored here. So, this is your tag area. Now, what we do? The word at address A is in the cache if the tag bits in one of the valid lines in the set index matches with the tag. So, what generally we do, once you get an address, we look into these portions of the address. What is the index bit and how will you get it? It is equal to the number of bits that is used to find out the total number of sets in the given cache. If the total number of set is say 1024, then 1024 is 2 power 10. So, 10 bits of the address is used for the set index portion. Go to that set index, it will give a number. In this context, it will give a number ranging from 0 to 1023. Let us say the number is 800. Go to 800 to set, check whether the valid bit is equal to 1. If the valid bit is equal to 1, check whether the tag is matching with this tag, whatever is being proposed. If it is perfectly matching, then that represents a hit. Once you know it is a hit, using the block offset portion, the word contents begin at offset bytes from the beginning of the block. So, what do you do to address a cache? First, you have to locate the set based on the set index portion of the address. Locate the line in the set where there is a tag that is perfectly matching. Wherever there is a tag match, check whether the valid bit is equal to 1 or not. If the valid bit is equal to 1, locate the data portion within the line based upon the block offset. Let me now draw your attention to a small numerical problem which will help you in understanding about this cache, tag, index and offsets concepts. Consider a cache that has 512 kilobytes capacity, 4 byte word, 64 byte block size and 8 way set associative. The system is using 32 bit address. Let us imagine there is an address 0xabc89984 is being given by the processor. Now, which set of the cache will be searched to find out this address and specify which word of the selected cache block will be forwarded if it is a hit in the cache. So, first we have to understand how many sets are there in the cache. So, I have a cache that has a capacity of 512 KB and the word is 4 byte and each of my block in my cache is 64 byte block and it is an 8 way associative cache. 8 way associative cache means your value of E, there are 8 blocks in a given set. The number of sets is divided by cache size divided by block size into associativity. Here you have a cache of 512 kilobytes, that is called 2 power 19. This is called 512 kilobytes divided by block size. Block size is 64 bytes, that is 2 power 6. Into associativity, it's 8 way associative cache, so it's 2 power 3. The answer is 2 power 10. You have to understand both denominator and numerator should be in bytes. So, one should not be in words. In this context, this word property is not used, we will use it a bit later. So, 2 power 10 is 1024. So, this particular cache has 1024 sets. Now, one word is 4 bytes. So, 64 byte block means I am keeping 16 words there because 16 into 4, 16 word, each word is 4 byte, together is my 64 byte that I am talking about. So, I have 10 bits for the index and I have 6 bit for the offset. Out of the 6, the first 4 bit will tell you word number and the next 2 bit will tell you what is the byte within that word. Anyway, last 2 bits is not relevant. If it is a 32 bit address, that is what it has been mentioned. Out of the 32 bit, the middle 10 bits is for index, the last 6 bit is for offset and the most significant 16 bit is used for tag. Now, what we are asking is in this given address 0xabc89984, that is the address that has been given here. This address I have to split into 16, 10 and 2. So, this black portion indicates, is it a hexadecimal? So, this black portion indicates it is a tag. The remaining 9984, that is a 16 bit value, since this is a hexadecimal representation, I am going to write that 9 bit value. The first 10 bits shown in blue color indicate the set index, then the 4 bit indicate the word number, that is the red color is word number and the green color is byte within the word. So, for this particular address, if you take up the blue portion alone, then the decimal value is 614. So, given this address, it is mapped to set number 614. Now, in 614 there will be 8 lines, that is why it is called an 8 way associative cache, it is clearly mentioned. There are 8 different blocks, we call it as 8 different ways. In each of the way, you see whether there is a tag match. So, this is your tag. If these 16 bit is stored in one of those 8 lines, then if you find a tag match, it is called a hit. If it is a hit, then extract word number 1. How you got word number 1? These 4 bits that is given in the red color, that will tell you what is a word number. There are 16 words possible ranging from 0000 all the way up to 1111. Similarly, one more example is given. Let us say if this is the address 0x485669AC is the address. I am writing only the red portion, that is set index portion and offset. So, the blue 10 bit will tell you what is a set number, then the 4 bit after that will tell you what is a word number. So, it is set 422 and word is 11. While designing of cache memory, there are basically 4 design choices. The first one, where can you place a block in the cache, and that has been defined by the block placement technology, and how a block is found if it is there in the cache or not, and that is called block identification. Third one, if you come to know it's a miss, then which of the block is to be replaced so that the missed word can be kept. That is called block replacement technique. And then when there is a write miss, what will you do? That is called write strategy. So designing of cache memory involves 4 different challenges. One is placement of blocks, cache placement, block identification, block replacement, and write strategy. Let us now go to block placement scenario. Consider you have a main memory that has 32 blocks. Block is nothing but continuous words. So if you have a main memory of 32 blocks ranging from 0 all the way up to 31, imagine that you have a cache. We call this cache as direct mapped cache, and let us say our discussion is on this particular block, block number 12. Any block in main memory is mapped to that block modulo 8, because I am talking about a cache memory which has 8 sets and each set has only one line. So I have 8 sets in my cache and each set has only one block, so altogether I have 8 blocks. So this block, block number 12, where it is going into the cache, that has been found out by 12 mod 8. 12 mod 8 is 4. So block number 12 get mapped to set number 4 in the cache. Similarly, block number 31, if I do, then 31 mod 8. 31 mod 8 is going to be 7. So this get mapped into 7. The problem here is, let us imagine I am going to bring 20 also. So 20 mod 8 is 4. 12 mod 8 is also 4. So now we are talking about 2 addresses, block number 12 and block number 20, both are mapping into the same location 4. That means contents of block number 12 and contents of block number 20 in the main memory cannot coexist in the cache. Such kind of caches where there exists a unique location for every main memory block, that is known as direct mapped cache. So there exists a restriction where can you place a block. On the other hand, if there is no restriction, I can keep 12 anywhere within the cache, that is known as fully associative cache. Both has its own pros and cons. Let me draw your attention into another mechanism by which it is being stored. You assume that the entire 8 blocks is divided into 4 sets and each set has 2 blocks each. Then my 12 get mapped into 12 mod 4. Why 4? Because I have only 4 sets, 0, 1, 2 and 3. I have 4 sets. So 12 mod 4 is 0. So the contents of block number 12 will get mapped into set 0. Now in set 0 there are 2 blocks, in either of the block you can reside. So it is a fusion of direct mapped cache as well as fully associative cache. This concept of different mapping technique in cache is very important. Let me draw an analogy what you generally use in real life. Consider the case that when you join in a college, let us say in the very first year, you all have notebooks. For each subject there is a notebook. So whenever that corresponding teacher enters the classroom, you are going to take that appropriate notebook. Let it be physics, then you have a physics notebook. When the mechanics teacher comes, you can go and take mechanics notebook. So every subject has a unique place. That is what is known as a direct mapping concept. Now think of a case in certain times, once you move up to the higher semesters, the same notebook may be used for 2 subjects. One you start writing from the front, let us say data structures, you write from the front, and other course is databases, you write from the other side. So both data structures and database, the same notebook is being used. That is called two-way associative notebook. Let us say when you move to final year, you may use the same notebook for 4 subjects. So you define the first 10 pages it's for this subject, next 10 pages like that. So for all these 4 subjects, this particular notebook is used. For the next 4 subjects, another notebook is used. Then with these 2 notebooks, you can effectively handle the whole semester. Whereas if you could have used separate technique, then you require 8 separate notebooks. That is called a 4-way associative cache. Similarly, I can think of 8-way associative cache where 8 different addresses are mapped onto that or 8 different blocks are coexisting, or 8 different subjects are coexisting inside a same book. And when you don't have any restriction at all, for any subject you can write anywhere, that is called a fully associative notebook. So I hope this example will give you a little bit of clarity about how this concept of placement, block placement, is introduced into the cache memories. So coming to cache block placement, the summary is direct map means a block can be placed only in one location, and let's been find out what is a block number in main memory modulo number of blocks in the cache. The second is called set associative, block can be placed in one among a list of locations. So in this case block number modulo number of sets in the cache. And the third one is called fully associative, block can be placed anywhere. Now little bit of illustration about direct mapped cache and set associative cache. Direct map is the simplest kind of cache. It's very easy to build. There is only one tag to compare. So once you get into a set, you know that that particular set has only one line. So you go and search whether the valid bit is equal to 1 or not. If the valid bit is 1, check the tag if it is same as the tag that you want. If so, this is your data. Using your offset, try to extract. So consider this case. Let's say in an example, I am interested in the set index value. Let's say the set index value is 00001. It's a 5-bit set index value, means I have 32 sets in my cache. So go to set number 1. That's the meaning of this. In set number 1, what are we going to do? So once you get the set index portion, once you reach that particular set, then first check the valid bit is equal to 1 or not. If the valid bit is equal to 1, then search the tag in the given address is same as the tag that is already stored there in the cache. The tag bits in the cache line must match the tag bits in the address. If that is happening, then that is known as a hit. And if it is a hit, that is if 1 and 2 both exist together, then it's a cache hit, and using your offset bits, you are trying to extract what is the word. If it is a cache hit, then block offset selects the starting byte of this word. This is how a direct mapped cache will look like in organizational level. Whatever is the address that you get from CPU, the physical address, you divide into tag, index and offset. Using index, using a decoder, will uniquely go in one particular set of the cache, extract the tag value. So tag value is extracted and it's compared with incoming tag, and if it is matching, it's known as a hit. So for matching, the valid bit also should be 1. And once if the match occurs, using the block offset, you could extract the corresponding word. That's all about direct mapped cache. Now coming to set associative cache, you know that this is a two-way associative cache where E equal to 2. So every set has 2 cache blocks. If every set has 4 cache blocks, we call it 4-way associative cache. If you have n blocks inside a set, then it is called n-way associative cache. So a set associative cache is characterized by more than one line per set. Now in this case, consider the case your set index was 0001 and that points to set number 1. Now once you go to this, let's say this is the address that is been given, and I have already selected the set. Now in this set I look whether both are valid or not. Yes, both valid bits are 1. Now what I am interested is whether my tag bit is 0110. The first one, the tag bit is not matching. This is a different tag, whereas in this case the tag is matching 0110. Once the tag is matching, this is the data that we are looking for, but I don't know from where I have to start. This offset will tell you from where to start. Here the offset value is 4, so start from byte number 4 onwards, 4, 5, 6, 7. Those 4 bytes will give you the corresponding word. So block matching is done by comparing tag with each valid line in the selected set. So valid bit should be 1, tag should match. If both 1 and 2, then it's a cache hit, and once if there is a cache hit, then what we do is word selection is done same as direct mapped cache by choosing the line that has produced the result or the hit. If it's a cache hit, then the block offset select the starting byte. So this is how a conventional two-way set associative cache looks like. You know that the address is being split up into tag, index and offset. Using index, you go into one particular set. In that set, this is the difference. In that set, you have now 2 lines. This is way 0 and this is way 1. Now parallelly in both the ways, I extract the tag value and the tag value is compared in both these cases, and the valid bit also should be 1. So if the tag is matching and valid bit is 1, then that determines whether you got a hit in this place or in this case. Effectively it's a hit, and using the offset, wherever you got a hit, the offset will return the corresponding data word or data byte. When it comes to fully associative cache, you don't have an index portion. The index portion will tell you where basically in which set you have to look into. So such a kind of a localized help is not available. You have to search everywhere. So what you do is go to each of the data block and then you perform the tag comparison everywhere, and then that determines the hit. If wherever or whichever place you get a hit, then that's it, you got it, but then you will take your offset value to extract the corresponding word. Okay, so to summarize that aspect, what we have learned now, we have learned about what is direct mapped cache, set associative cache and fully associative cache and its functioning. The concept of division of set index, the set index is used basically to locate or to localize your search inside the cache memory. So in a cache, we are not going to search the entire location. From the address, a property of address, which is nothing but few bits in the address are being extracted out, and these bits will tell you where to look into the cache. And once you go into the location, this tag will tell you whether the data that is stored there is same as what you are looking for. And once you get the hit, then using the offset you try to extract. Let us now try to understand what is the complexity involved in locating one particular index. So this cache indexing, let you look at, in the address our first duty is to find out the set index. It's a few number of bits, and these bits, so in this case you have 5, so it's basically 5 bits are being passed on to a unit and they will choose one among the 32 sets. So it is basically a 5:32 decoder. So decoders are used for indexing, and indexing time depends on the decoder size. So we have a decoder whose size is S is to 2 to the power of S. So when you have smaller number of bits in the set index, the decoder that you are going to use is of smaller size. That means effectively the time to decode is less. You will reach the cache memory faster. So when the cache memory is big, meaning that you have more number of sets, it will take more time to index, because you are using a big more complex decoder, it will take more time to return the word. So smaller number of sets, less is the indexing time, less is the cache access time. Now out of these 3 combination, that is tag, index and offset, why I am using the middle bits for indexing? Why can't I use the most significant bits for indexing? You know that out of the given address, the offset portion are the bits which will vary for the bytes within a block. Let us now not discuss about it. I am now more interested in this tag and index portion. So this tag and index portion together define your block number in main memory. This is the offset within a block. So this portion, tag and index, together defined what is the block number inside main memory. So consider I am talking about a 4-line cache. Let us say I am going to give the sets as 0, 0, 0, 1, 1, 0 and 1, 1. Now consider my main memory if I am using higher order for indexing. So consider higher order for indexing. Let us say I am having a main memory of total 16 lines, and let us say these are the addresses given to the lines or line numbers basically. If we use the most significant bits for cache mapping, all lines whose most significant bit is 0, 0 will get mapped into this set. All lines whose most significant bit is 0, 1 will get mapped to the yellow set, and 1, 0 will get to set number 1, 0 and 1, 1 will get mapped to set number 1, 1. So it is a higher order bit indexing that is there. So what happens is your adjacent memory lines would map to the same cache memory. So consider a case that you have a music program that is residing inside your main memory. Now the first line of the music program, to play it I have to bring it to this block. once it is over, let us say the address goes to the very next location, even though my remaining 3 blocks in my cache memory is full, it will evict out the previous one, because the second one is also mapping into the same location. So, it will evict out one and then only it will bring next. So, this is actually a poor use of spatial locality. That means the nearby blocks will evict the just immediate block. So, as the entire pink region will occupy one place in the cache, one at a time. The entire yellow region will occupy only one place in the cache, this yellow portion. If you are using lower order bits for indexing, that is the middle order bits for indexing, then it is a better usage of spatial locality. You can see that if these 2 bits are being used, then these are the blocks that get mapped into the same location. They are not adjacent to that. So, consecutive memory lines are actually mapped into different lines. If you look at here, they all are mapping to different lines. This is better use of spatial locality without replacement. In this case, we have a lot of replacements, whereas in this case, such a kind of a replacement is not happening as we move to adjacent locations. So, with this we come to the end of this lecture, where we had a quick introduction of the concepts of cache memory. Over the next lectures, we will be moving into slightly advanced concepts of cache. Kindly go through the textbook and the video material multiple times. If there is any query, please let me know. Thank you.